So the question is not one of whether a ball that is thrown is legal or not. When we look at the data, we simply care about, is it 6 feet? And can we use the data to prove that? But we certainly know that it makes sense intuitively that, a ball that reaches 6 feet in height, if it's thrown really fast, then it's going to go way past the plate. And if it's thrown, really, really slowly, then it's going to be short because it has to reach that height. So there's a battle, there's a tension between the speed that the ball is thrown, the distance that the thrower is at, the height at which the ball is released, the size of the plate, and the 6 foot minimum peak that a thrown ball has to have. And if we can control some of those variables, then maybe we can get a better idea of what a ball in a legal pitch rather is like. And I think we can do that with the data. So what I've done is I've done some data sampling based upon some of the videos you saw. You would see me pitching balls, and during that time I was actually measuring data. I have a little radar gun that I was measuring speed with. I know the distance that I was pitching at, and I had the height being measured as well, or at least the minimum height. And so we can see, we can plug in a lot of that data into mathematical formulas that clearly define the trajectory of a ball. Now this particular site, which is, hopefully will come into focus, I'll put the URL for this site in the video notes. But this particular page has some interesting formulas in it. It has one is, will it clear the fence? And it's not really about will it clear the fence, because in this example you see here that the ball is being launched from the same height that it's landing. So yes, we are interested in a 6 foot fence, but we're interested in a fence where the ball is released at around, as you can see here, the ball is released at around the hip height, which for a 6 foot pitcher is about 3 feet. And the ball lands on the plate, which is on the ground, so 3 feet lower, right? So what we're really interested in is this question here, is where will it land? So in this particular equation, if we know the velocity and the angle, then we can see what the height is here. But we already know, sorry, if we have all three, the height, the velocity, and the angle. The velocity is easy to figure out if we have a radar or a stopwatch and we know the distance. And the angle, well, the angle can vary. Maybe we can look at what range the angle could be in. And so that's what I started working with. Now it should be noted, if you plan on using this chart, when you look at the data, the x2 measurement, which is given here, is this line. It's the actual line, the horizontal distance from the release point to the time it hits the plate. The x1 distance, it doesn't really say exactly what x1 is here, but it could either be this distance, the difference in the horizontal distance from where it crosses the launch height and where it crosses the actual landing point. So it could be this short distance here, or it could be the distance of where the ball would have been launched from had it had the same height as the landing point. Either way, you'll see that x1 ends up being a negative number, it's a smaller number, and x2 ends up being the number that we're interested in. Okay. So when I plug in my data, what I was doing is I was basically hypothesizing and testing out different theories. The first theory I had was against 35 miles an hour. And then I tested for 30, and then I tested for 25, and then I tested for somewhere in between, which was 27. And through my data gathering, data collection, I learned that on the radar gun, I was throwing consistently 26 or 27 miles per hour, which is over here. And the radar gun, it measures horizontal speed, whereas the formulas, they want you to put in the launch velocity. So given an assumed launch velocity, this is what the horizontal speed ends up being. And this is just a fact of the ball traveling through the air at a given distance over in a given time. We can measure the speed. So I basically settled upon 30 miles an hour being the launch velocity, and the real velocity that you measure by radar ends up being in this range. Now, why 30 miles an hour? Well, when you pitch it at a faster speed or a slower speed, you end up with different landing points of the ball. And I could see that, we were trying to hit the plate. We're trying to get within 1 foot, let's say maybe 2 feet of the plate. Anything else is going to be very obviously a ball and not even worth bothering about. So we need it to be within a certain range. Now this particular column here, this is the range that the ball needs to travel. And I would plug in the data into the formulas on the other page, and basically it would spit out the height that the ball would travel, and I would test various angles against the velocity that I've known to throw. And the angles that ended up returning distances that would be relevant to a batter swinging at were these 4 rows here. Okay, so we're talking about a range of 26 to 28 miles an hour and a launch angle ranging in 21 to 27. So that's what the data told me. It's interesting that when I went out and actually measured the speed, that it was that speed. And when I went out and I actually measured the angle, it was about 23 point something degrees consistently. So, what about these distances? Why do they look wrong? Well, the distances here, the top one says 48 feet, 45 feet, 43, and 40. These are the distances given by the formula where the ball lands at the same horizontal plane that it's launched from. If you adjust for a plate being lower than the release point, then these are the adjusted distances. And you notice here that 50.6 feet and 49.5 feet, that's right around the front of the plate. And that is the sweet spot of my measured angle and the sweet spot for my measured speed. It's not a coincidence. This data, it's science, and so it makes sense that the predicted values would match what I actually found. Now it's important to notice another thing here is that we want to convince people that even short pitches are okay. So even this pitch, which is as short as 46.7 feet, that's that's like 3.3 feet short of the plate, is still 3.8 feet above the release point. So that's why these heights look wrong. You have to add in the height of the release point. I'm releasing the ball at my hip, which is 3 feet at least, 3 feet point something. So you can add 3 feet to all of these. So this is 6.8 feet, this is 7.6, this is 7.98, this is 9.21. So again, if you look at the 2 most interesting data points where I'm hitting the most often, it is clearly above 6 feet. We're talking the 7 to 8 foot range, and I'm being called I'm being called illegal pitches consistently. Now you can go ahead and plug in your own data, or I'd be happy to send you more of the data from other speeds that I measured. I'd be happy to go and do a test with anyone who wants to go out on the field. I'd be happy to sit behind you while you umpire a game and track your progress and then review what actually happened against what you think happened at the end of a game. I think that we can improve what's happening, and I think we can empower umpires to make their job easier and make it a win-win. Make pitchers, have more clear expectations of what the result will be. So thank you for listening, and please watch the other videos which show the actual pitches themselves, and please give me some feedback.